Okay. So this is the problem. Here I have given a circuit which consisting of two resistors. One is a 5 ohm resistor. Okay, one is a 5 ohm resistor and other is a 8 ohm resistor. So here I have no, one is a 12 ohm resistor. Here I have three resistors and one capacitor. The value of the capacitor is 0.1 farad. So here in figure, let VC of 0. This VC of 0 indicates the voltage across a capacitor under initial condition. Okay. So find VC, the voltage across a capacitor, and V voltage across a 12 ohm resistor, and Ix for t greater than 0. So this is my problem. So here I want to find out the find VC, Vx, and Ix for t greater than 0. For t greater than 0. So here for t greater than 0. So first, so here this is my circuit. I want to find out the voltage across a capacitor and voltage across a resistor, 12 ohm resistor, and current to this 8 ohm and 12 ohm resistor Ix for t greater than 0. So before going to the problem, I will explain some simple logic how the capacitor and how the inductor is behaving. So for example, it is the inductor. Okay. So for the current flowing through it is I. The current flowing through it is I. The voltage across the inductor is V. So what is the voltage and current relation for the inductor? The voltage and current relation for the inductor is given by VL equal to L into di by dt. So voltage across the inductor is given by VL equal to L into di by dt. So for example, okay. So here this statement can be said that the inductor doesn't allow sudden change in current. So L doesn't allow, okay, sudden change in current. Inductor doesn't allow sudden change in current. So it means, for example, so here this is the VL equal L into di by dt. So where I is the di by dt is the change in current, dt is the change in voltage. For example, the inductor allows 0.001 current. Okay. So if the inductor allows the change in current, di is, for example, di equal 0.001. There is a small amount of current within 0 seconds. So within 0 seconds. Okay. So for the current is equal to 0.001, the change in time is 0 seconds. Okay. So it means, so something by 0 is definitely infinity. So it means VL equal L into di by dt. So it means VL equal infinity. VL equal to infinity. So whenever the voltage across the inductor is equal to infinity, in that case only the inductor is allows sudden change in current. But practically it is not possible. So it means the inductor doesn't allow sudden change in current. So I am repeating my statement again. Inductor doesn't allow sudden change in current. Because so for the sudden change in current, the inductor requires infinity amount of voltage as an inductor. The infinity amount of voltage providing as an inductor is not possible practically. That's why inductor doesn't allow sudden change in current. So means, for example, here, for example, I am considering this is my inductor. Okay. So for example, it is the inductor. This is the inductor. Okay. So it is the inductor. The current flowing the inductor is I. Okay. So here inductor. So the current in the inductor is up to for example in the inductor is suddenly cannot be changed. So if for example under steady state current conditioning the current is like this, this is the steady state current. So if it is an inductor, the current is gradually increases. For example, at t equal to 0, for example, but at t equal to 15, it is t equal to 15. So, for example, the current is cannot be changed instantaneously. It is gradually and up to this point the current in the inductor is 0. Now, it cannot be increased from 0 to this 15 instantaneously. So it cannot be possible. Inductor current is cannot be increased from 0 to this whatever the magnitude instantaneously. So it takes the power gradually increases. Okay. The same time, the current gradually decreases. For example, it is at 15 times, it can't be reduced to zero value instantaneously. It is gradually reduced. Okay. Gradually reduces. So inductor doesn't have sudden change in current. So it may be increases gradually or decreases gradually. The inductor cannot be changed from 0 to some finite value instantaneously, or it cannot be fall from finite value to 0 instantaneously. It is gradually happening. It is gradually increasing or gradually decreasing. So this is the one case. Coming to the other case. Now it is a, for example, capacitor. It is a capacitor. The current flowing to the capacitor is say I. The voltage across the capacitor is C V. So here the voltage relation for the capacitor is given by I equal C into dV by dt. So this implies that so capacitor doesn't allow sudden change in current. Sudden change in voltage, not current. Sudden change in voltage. Sudden change in voltage. So inductor doesn't allow sudden change in current. At the same time, capacitor doesn't allow sudden change in voltage. Here, this example also indicates that. For example, here the current through a capacitor I is given by I equals C into dV by dt. Here I am considering. So here I am considering the C value is what is as t. For example, there is a small amount of current, let us say 0.0001 within 0 times indicates which is equal to I equal to infinity. So whenever the infinity amount of current flowing to the capacitor, at that case only the capacitor allows sudden change in voltage. But practically we cannot provide infinity amount of current through this capacitor. That's why capacitor doesn't allow sudden change in voltage. So the capacitor doesn't allow sudden change in voltage. Okay. So keeping these two things in mind, okay, I will. So here in this transient condition, you can see there are two conditions. For example, here I'm transients. Here I'm considering this is the change in current I. Okay, okay, change in current I. This is the current I. So I'm taking the time. It is the time t. So it is time t equal to infinity. It time t equal to minus infinity. It time t equal to 0. Okay. For example, at t equal to 0, at t equal to 0, at t equal to 0, which is the switching instant. At t equal to 0, which is the switching instant. At t equal to 0, which is the switching instant, means at t equal to 0, I am closing the switch or opening the switch. I am closing the switch or opening the switch. For example, if you have a circuit is like this, okay. So this is a 2 ohm resistor, 3 ohm resistor, is 500 capacitor, and which is a, for example, the switch. This is a switch which is closed at t equal to 0 or open at t equal to 0. Okay. So this is the some 2 volt source. So this 2 equal to 0 is called switching instant. this two equal this is equal to, this is called switching instant. So here at t equal to 0, this is at t equal to 0. This t equal to 0 indicates it's a switching instant. Okay. And this is a t less than 0 before the switching instant, and it is the t greater than 0 after the switching instant. So for this particular problem, I am closing my switch at t equal to 0. Okay. So let us consider like this. Okay. Okay. For example, I am opening the switch. So here, for example, my circuit is given like this. Here I have some 2 volt source, 2 ohm resistor, 3 ohm resistor, and 5 amp resistor. Here I am opening. I am not initially the switch is closed for a longer time. Okay, the switch is closed for a longer time. This is the switch which is t equal to 0. So if the switch is closed for a longer time. So the switch is closed for a longer time, and now it is open at t equal to 0. And it is open at t equal to 0. So here this t equal to 0 is called switching instant. So how the circuit is behaving at t equal to 0? Here this is my circuit. At t less than 0, how the switch is how the circuit is look like. At t less than 0, my circuit is at t less than 0, the switch is in closed position. The switch is in closed position. It is appear like this. Okay. So it is a 2 volts, it is a 2 ohms, and the 3 ohms, it is a 5 mA. Okay. So for a long time the switch is for t less than 0, the switch is closed for a longer time. This is my circuit. It is called t less than 0. At t equal to 0, at t equal to 0 means switching instant. The switching instant, this is open. Okay, this is open, which is like this. It is open. Okay. So at t greater than 0 also, at t greater than 0 also, at t greater than 0, at t greater than 0, if the circuit is like this only. Okay. So here, these two things, just keep these two things in mind. So how the circuit is behavior at switching instant, how the circuit is behavior at the after the switching instant and before the switching instant. So okay, this is the t equal to 0 instant, and this is the t less than 0 instant, and this is the t0 instant. Okay. So it may be either current or voltage. It may be either current or voltage. So it may be the variation of the current or voltage. Okay. So for this particular problem, so for example, it is an inductor. So for example, for inductor, here you can define two conditions. So for example, I0 means it is the switching instant. So I0, which is the switching instant. Okay, I0 is the switching instant, and I0 minus is a before switching instant. I0 minus is a before switching instant. I0 plus is the after switching instant. So here if you observe all these things, I0 is the switching instant. Okay, what is the current at t equal to 0? I0 minus is the just before switching instant. Just before switching instant. Just before switching instant. It is at switching instant. Here this I0 plus is nothing but just after switching instant. Just after switching. So, for example, if you are dealing with an inductor, you have to take care about the current. So, variation of the current, because so the inductor doesn't allow sudden change in current. So, you have to take care about how the inductor current just before the switching instant and just after the switching instant. So here this I0 means indicates the current at the switching instant. I0 minus indicates just before the switching instant. I0 plus indicates just after switching instant. So here all, if you observe all the three terms, all the three currents I0, I0 I0. So all at zero instant just before, just after. So as you know, inductor doesn't allow sudden change in current. So that's the case. I0 plus and I0 minus all are equal. All are equal. So this is called initial condition. Initial condition of your circuit. Initial condition of initial current of your inductor. Initial current or initial condition. You can call initial condition or initial current in the inductor. Okay. Like that, for example, it is a capacitor. For capacitor. So here I am closing the switch at t equal to 0. At t equal to 0. So let us say V of 0, what is across a capacitor? V0 minus and V0 plus. So here this is a voltage across the capacitor at switching instant. Voltage across capacitor at switching instant. Okay. At switching instant. Here voltage across capacitor just before switching. Just before switching. Here just after switching instant. Just after switching instant. So as you know, so RR voltage at t equal to 0. At t equal to 0. But here I am giving 0 minus, 0 plus and 0. So 0 is the switching instant, 0 minus is the just before, 0 plus is the just after. So within 0 time the capacitor cannot be allow sudden change in voltage. So that's the case, both are equal. V0 minus V0 and V0 plus all are equal. These are called initial conditions of your capacitor. Initial condition of capacitor. So initial condition of capacitor. It means, for example, if you have a circuit is like this. Okay. So I am closing the switch at t equal to 0. At t equal to 0, the capacitor has some voltage which is given by some 15 volts is here. Okay. So 15 volts is here. So if it is gradually decreases, and at t equal to some at particular time, which is essentially reduced to 0. But here this is called T0 plus and this is called T0 minus. Okay. So for example, if the capacitor voltage is like this, okay, if the capacitor is voltage like this, so T less than 0, capacitor has 15 volts. Okay. T greater than 0 and the capacitor has 0 volts. So this is the T less than 0 area. So T less than 0 and T equal to 0 and T greater than 0 area. So at T less than 0, the capacitor has a 15 volts and at T greater than 0, the capacitor has 0. So this is the switching instant. After the switching instant, the capacitor current is gradually decreases. So as I said, the capacitor cannot be reduced from finite value to 0 instantaneously because a capacitor doesn't allow sudden change in the voltage. It is gradually decreases. Okay, so this is like this, but at the switching instant, this is a t equals 0. At the switching instant, so just t equals 0. T0 minus means it is the t less than 0 instant. Just before is the just before, and t0 plus is the just after, just after, and t equals 0. So at the t equal to t0 minus, at t0 minus means before the switching instant, what is the current here? What is the voltage across the capacitor? 15. Okay. So at t equal to 0 also, the voltage across the capacitor is 15. At t equal to 0, just after voltage across it is 15. So we can say V of 0 equal voltage across the capacitor under initial condition is given by 15 volts. With this is the t equal to 0. This is the t equal to 0. So like that. So while we are solving the problem, we should take care about the initial conditions of the capacitor as well as initial conditions of the inductor. So how can you find out these initial conditions? By considering just before, just after the switching instant. Okay. So with this example, I am going to solve one problem. Yes. So this is my problem. I want to find out the So here this is my problem. I want to find out the Vc and Vx and Ix for t greater than 0. So here, first of all, so here I have a let. Here this means let, this is the problem. Let Vc0 equals 15 volts means the voltage across a capacitor at time t equal to 0 has a 15 volts. So what is the voltage across a capacitor at t equals 0? So voltage across a capacitor at 0 is given by 15 volts. Okay, 15 volts, which is the initial voltage. Okay, so here it is a just say me just say tell me it is a voltage across a capacitor is acting as 15 volts. Now is it a source free circuit or a forced circuit? The given circuit is a source free circuit or forced circuit. 33. So this is the source free circuit. Okay, right, Amma? So source free circuit. What is the initial voltage across the capacitor? What is the initial voltage across the capacitor? What is the initial voltage across the capacitor? The initial voltage across the capacitor is 15 volts. Okay. Now, so the initial voltage across the capacitor is 15 volts. So here, this capacitor is acting as a voltage source and it can deliver the energy. But up to it cannot be this voltage. This capacitor can deliver for the short period of time. How it can be this capacitor has some capacity. Okay, so during it depends upon this capacity, it can store the some energy. So it can deliver the energy to the some external circuits up to some time. It cannot be deliver the energy to the some external circuit over a infinite interval of time. So that's why we can call it is a source free RL circuit. Okay, so here the source free RC circuit, the source free RC circuit we have. So the response, the final response of it is consisting of a transient response both transient and steady state response. What is the response of the circuit? Is it contains both transient, steady state, or only transient itself? So here it is a source free circuit. So what is the final response of the source free circuit? Only the transient response. by time constant. So whenever the transient response is coming to the picture, find out the time constant value. Okay, you have to find out the time constant value. So here, what is the time constant of series RC circuit? Now it is a series RC circuit. What is the time constant of RC circuit? Whatever it is, a series RC or whatever. What is the time constant of RC circuit? What is the time constant of RC circuit? Now, this circuit is act like a, it is a source free RC circuit. So whenever the source free RC circuit is taken, whenever the source free RC circuit is there, so whenever the source free RC circuit is present, you can get only the source free. The source free RC circuit, you get only the transient response. You can get only the transient response. You know, the response of series RC circuit is given by voltage across a capacitor is given by Vc of t equal V of 0 into e to the power of minus t by tau. So this expression can already have known from this your circuits. So voltage of series RC circuits. Okay. So voltage across for series RC circuit, voltage across the capacitor is given by V of 0 minus e to the power of minus t by t. This is the initial condition. This can be obtained by initial condition. Okay. So here now I want to find out this time constant tau. T is the time constant. Okay. So T is given by R equivalent into C. So you know what is the time constant of series RC circuit or parallel RC circuit? Just R into C. But here, how many? Here instead of single resistor, you have a three resistor. So 5 ohm resistor, 8 ohm resistor, and 2 ohm resistor. So to find out this time constant, you need to find out the R equivalent. How can you find this R equivalent? R equivalent across capacitor terminals. Across capacitor terminals. What is the R equivalent across the capacitor terminals? Just find out the R equivalent across the capacitor terminals. Find out the R equivalent across the capacitor terminals. So if you find more than one resistors, you need to find out the equivalent resistance across the inductor or equivalent resistance across the capacitor. So what is the equivalent resistance across the capacitor? Anybody? Okay, Madhavan, write them up. So only one person has answered. What is the voltage across the 4 ohms? So what is the voltage across this capacitor? 4 ohms. So so you need to find out the voltage across this 4 capacitor. What do you do? What do you need to do here? So to find out the voltage across the capacitor, so here you need to find out the voltage across the capacitor. You need to find out the here you want to find out the this voltage across this equivalent resistance capacitor. So you want to find out the equivalent resistance across capacitor. So find out the voltage. Here this is the AB. So here these two are connected in series. These two are connected. This one is connected in parallel. So R equivalent equal. So this is 12 plus 8, that is 20 into 5 by 20 plus 5. You can get R equivalent equal 4 ohm resistor. Okay. So what is the time constant here? What is the time constant? Time constant is given by time constant is given by R equivalent into C. Here R equivalent is and C is a 0.1, it is 0.2. So you can get the 4 seconds. So this is the time constant. Okay. Once you find out the time constant, so here here so this is act like a now I want to find out the Vx, Vc and Ix. Okay. For t greater than 0, Vx, Vc. So here the voltage across the capacitor. After reducing this circuit, how can I draw my circuit? It can be drawn like this. This is the C and this is the R equivalent. Okay, this is a C. Now it is the S minus Vc, Vc, Vc of t. So this Vc of t is given by so V of 0, what is the initial voltage across the capacitor, and e to the power of minus t by tau. What is the tau? Tau equal R equivalent into C. So here you can get this is a 0.4. Okay, zero point 0.4. Here you can get the response Vc of t is given by what is the voltage across the initial condition? I said Vc of 0 equal 15 volts. 15 and e to the power of minus t by 0.4 seconds. You can get 15 e to the power of minus 2.5 t. 2.5 t, which is the voltage across the capacitor. So voltage across the capacitor here we can write voltage across the capacitor is given by 15 e to the power of minus 2.5 t. So this is the voltage across the capacitor for t greater than 0. Voltage across the capacitor for 0. Next here you want to find out the next once you find out this voltage across the capacitor, you need to find out the this voltage across the capacitor. So voltage across the once you find the voltage across the capacitor, now you can easily find out the voltage across the resistor. So this Vx is given by this Vx. So here do you know already you know about the voltage division rule. So voltage division rule states that so voltage here whenever the voltage is connected three series connected elements, the voltage can be divided by using current division rule. So here the voltage across this voltage across the capacitor is given by this 15 e to the power of minus 2.5 t. Now this voltage across the capacitor. Now this voltage is connected in series to the 8 ohm resistor as well as 12 ohm resistor. Here you can apply voltage division rule. As per voltage division rule, the voltage across the capacitor, the voltage across this 12 ohm resistor is given by the total voltage into the value of the resistors, which is 12 by 12 plus 8. Is it right? Okay. So from this you can get a 0.5. This here you can get 9 into e to the power of minus 255 t into this is the voltage across the capacitor. Okay. Now, so voltage across the here voltage across the capacitor is given by this one. Voltage across the 12 ohm resistor is given by this one. And now what is the current flowing through this one? The current is Ix is given by you can write Vx by 12. or we can x by 12. It get given that is 9 e to the power of minus 2.5 t by 12. Okay, here you can get 0.75 e to the power of minus 2.5 into t. Or you can get Ix is given by Vc of t by 8 plus 12. You can get what is the Vc of t. So Vc of t, this is the Vc of t. Here you can get this is the Vc of t, voltage across circuit. You can get voltage across these 2 points is Vc of t by 8 plus 12. What is the Vc of t? 15. 15 e to the power of minus 2.5 t by 20. By 20, you can get the same answer. This is also equal to 0.75 e to the power of minus 2.5. Okay, here there is a small announcement. Here I got a notification, the meeting will be in soon. So all of you just leave the meeting and rejoin again. But before we leave the meeting, all of you drop your roll number in the chat box and then just leave the meeting and rejoin again with the same link. But